Hey folks, today I'm going to talk about Rust and Python. I'm going to talk about why I sometimes use Rust, even for projects where I might have used Python. So for some people, this is going to be an introduction to some Rust features, right? We're going to talk about some of these features that might be new to some people. But I also want to focus on the bugs that these features help us catch, because I want to use this as a chance to tell sort of the other half of the story of why I think Rust is as hyped as it has been. Rust has been very hyped for about 7 or 8 years. And I think there's kind of two sides to that story. And I want to tell the side that I don't usually get to tell. So I'm going to do that by talking about Rust and Python. I have already recorded this talk once, and that was the slow version. And that was about an hour and a half long, which is too long for most people. But if you prefer it when I talk more slowly, or if you might not be as familiar with Python and going line by line is helpful, I will link to that version in the description. This is going to be the fast version, and I'm going to try to get it in about 45 minutes. We'll see how that goes. But we're going to be talking about some of these features of Rust and the bugs that they catch for us. So usually when I'm introducing Rust, and the most common story that we tell when we introduce Rust is this story, right? Rust is one of these. These are the native languages, right? These are the languages that win the benchmarks game on the internet. These are the languages we use when we program a toaster or whatever, right? There are a lot of things that only native languages can do. And there were about 30 years there where C and C++ had like no competition in this space. So of course, it is very exciting that Rust has come along. There's a third option, at least one third option in this space. There may be more soon. That's an exciting story. And these languages have had memory safety problems for a long time. So it is interesting and exciting that Rust has features that help us with that. We tell this story a lot. This is certainly the biggest part of why Rust is as hyped as it is. It's not the story I want to tell today. The story I want to tell today is this story. How does Rust compare to these languages? These are the managed languages, the garbage collected languages. Most popular languages are in this category. Probably most of the people listening to this video know at least one of these languages or the languages that are like these. And these are the languages that we usually choose when we just want to get our work done, right? The story for a long time was that if we don't have to choose a native language, we probably choose a managed language, right? If we don't have to have that speed, if we don't have to program a toaster or whatever, then we're probably using one of these. That's been the story for a long time, because when we use native languages, when we use C and C++, we have to deal with these extra bugs that come with the memory safety stuff. We have to do more work to get our work done. And if we don't need that speed, that trade-off is not worth it. That was the story for a long time. But I think the story with Rust is in some ways the opposite. So Rust definitely has a learning tax. It is harder to learn than any of those languages in the previous slide. You have to learn a lot of those native language concepts. But instead of giving you more bugs to deal with, Rust is going to erase entire categories of bugs that we are used to dealing with, even in those managed languages. So yes, of course, the managed languages don't have to deal with memory corruption bugs. That's nice. But there are a lot of other bugs that we deal with every day that Rust can just make go away. And that means that Rust can make sense as an option. We can consider using it, even in a lot of cases where we don't need we don't need a native language. We don't need that speed. It can still make sense to consider Rust as an option just to help us get our work done by catching all these bugs. And I think that's the other half of the hype story. Yes, the native language side of things is the big half, but this is the other half of why people get so excited about Rust, because we see all the bugs that it catches for us and we start wanting to use it everywhere. So we're going to start talking about 3 big features of Rust, and in particular about the bugs that those features help us catch. Let's launch right into it. So we're going to talk about enums, Rust enums, and how those help us catch null pointer bugs, right? Let's get started. So I've thrown some Python code on the slide. It's too much to read. Don't read it now. I'll zoom in on it. I'm throwing this on here so that we have some code that uses null pointers, what Python calls none, right? The null object. So we can talk about that and talk about some examples. I want you to feel free to imagine this was Java or Go or Ruby, right? Whatever your favorite managed language is, feel free to mentally translate all this code as we go from Python into that language, because the points that we're making here are going to be just about exactly the same in most of these languages. I've picked Python just to pick something, but it doesn't have to be Python. Everything we're saying applies to the whole group. So we have a program. We're going to look at it real quick. It doesn't do much. It's just going to let us talk about null. So calling it scream, it screams hello world. Okay. And it can take a path. And if we give it a path, it writes to that path instead of to the terminal. Fair enough. So zooming in, we have the screaming output class. It takes a path. That path is optional, right? This is how Python represents optional. It might be there. If it's there, we open it and we have a file. If it's not there, we don't have the file. When we use that file on the inside, we have to check whether it's there, right? So there's these two modes that we can be in. That's where the screaming happens, just for fun. And then when we create the screaming output, there's two ways to create it. And we look at the arguments, argv, right, is the command line arguments. And if we got one, we create it that way. If we didn't get one, create it the other way, and we write to it. So that's it. And we've used none. We've used that null to represent the path that might be there, might not be there, to represent the file that might be there, might not be there. And most of us have learned one of these languages, and we're all familiar with null pointer bugs, right? Null pointers are the $1 billion mistake, and we call it that because these bugs are very common, right? If we forget to check the path, we get a crash, right? If we forget to check the file when we use it, we get a crash. These are about the same bug. These are runtime bugs, right? We get these bugs when we run our programs to the point where we made the mistake. So we often try to write a lot of tests to catch these bugs, and it's a lot of trouble. Let's see what Rust does. So we have the same program on the right, cargo, of course, the Rust build system, doing the same things. -q just gets rid of some logging, quiet mode, and then we have this optional argument. So instead of using null, Safe Rust does not have null. We use what's called enums. And you might be familiar with enum as a keyword from C or Java. Many languages have something like this. Python has the enum module. You can import enum. And in those languages, enums are all about giving names to numbers. It's a relatively lightweight feature. In Rust, it's much more interesting. So in Rust, our screaming output can be in one of two states, file and standard out. And maybe that's like the enums we're used to. But here's the difference. In the file state, we have this field. We have this member, which is also called file, and it's of type file. So if we're in the file state, we have this open file handle. And if we're in the standard out state, we don't have that. So enums in Rust can have fields, and those fields are specific to the different variants of the enum. Here's what it looks like to use that. So when we use an enum, self, here's the screaming output. There's the screaming, just like in Python. And when we use self, we use that enum, we match on it, right? So the folks who have some Rust experience are, of course, familiar with this. But a lot of folks are seeing this for the first time. When we do a match, it's kind of like a switch. If you've seen languages that have the switch keyword, we name all the variants of the enum. We have two of them. And each of those variants gets a block of code. And depending on which variant we have, that's the code that we run. And here's the key thing. In the file mode, the file variant, we name the field, and that file is in scope. And that file is not in scope here. Okay, so it's sort of like the file is there or not, just like in Python, but it works differently. Here's a very quick overview. This is probably too fast for folks who haven't played with enums in Rust, but I want to highlight that there are a lot of enums and we use them all over the place. So screaming output, that was our custom enum with file and standard out. But we also see option here. That's how Rust is going to represent this path. I call it maybe path, this path that might or might not be there. It's a string, but it might not be there. We call that an option string. An option is an enum. It's a standard Rust enum. And we match on it, just like we matched on screaming output. So when we match on it, these are the two things it can be, right? It can be some or it can be none. And if it's some, you have data. We call it path here, and path is in scope for this block, but there's no path here. So it's very similar to our custom enum, but this is a standard tool of the language. This is how we represent values that might be there or might not be there in a very general way. And while we're here, I just want to highlight that we also see result. This is how error handling is done. I'm not going to get into it. It would take too much time to get into exactly how error handling works, but we can just mention that result is also an enum. So like option can be some or none. Result can be okay or error, ERR. And we see some of those okays here. So these are results. And this question mark operator, again, not getting into the details, but just at a very high level, this question mark operator is how Rust handles errors, and it is a shortcut. It is syntactic sugar for a match, just like this one, but it's matching on results. And in the error case, it returns the error. So I just mention all this to emphasize that we use enums all over the place in Rust. They are not a niche feature at all. We use them constantly. And it's perfectly normal to have a function just like this one that has 3 different enums doing 3 different things, right? So that's enums in Rust. Now, when we make the same mistakes in Rust that we just saw in Python, right? We forget to check whether we have the path or not. It looks like this. And this is the same mistake, but we see it coming out of cargo build. So cargo run will do the build by default. Here I'm doing the build explicitly because I want to emphasize these are build time errors, right? This is like making a type error, right? It's like passing the wrong type to a function. Most of the managed languages that we looked at on that last slide, those 6 that we picked at random, don't distinguish between the type of a value that might be null and the type of a value that's definitely not null. Right? Those are the same type in Java or in the languages that don't have static types like Python and Ruby. Rust distinguishes that. It's not the only language that does. A lot of the more modern managed languages like TypeScript, right, will have different types for the nullable values. This is a more modern feature. Most of the managed languages don't help us out with this. Here's the same mistake. We forget to check the state of the self enum in the write method. Maybe we imagine that self has a file field and we can just use it directly. Self does not have a file field. The only way to access the file is to match on it, right? This isn't even a type error. This is just a name that doesn't exist. Right. So Rust is very good at helping us remember to check the things that we need to check. Now, my favorite thing about enums is how they help us grow our programs. So in this case, I've taken the screaming output enum and I'm just imagining that I'm adding a couple features, right? I'm adding the path. I'm adding a third mode, standard error mode. Then what we see when we make changes like this is we build the code and the Rust compiler goes boom, 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 boom. It gives us this whole big list of errors. And these are happy, helpful errors. These are not angry, frustrating errors. These are helpful errors because Rust is telling us all the places where we need to update the code to match the change that we just made, right? To make the corresponding change at the sites where we use the enum. So when we create this file mode screaming output, hey, previously we were just passing the file, but now we've said there's also supposed to be a path here, right? We need to put the path here. Rust is going to tell us that. When we were matching on self, previously we had file and standard out. And we had blocks for each of those. And Rust is going to tell us, hey, you've added this third mode here. Yeah, that's great. But now you need to go tell me what to do in this mode. So Rust is going to highlight for us all of the places where we need to make the corresponding change. And it's pretty common as you get more experience with enums in Rust to just use this as your workflow, right? You make a change and then you just look at the compiler errors and that reminds you of all the places you need to update. My favorite way to think about what's happening here is that we are able to tell Rust exactly how many states this object should be in, right? This object should be in one of 3 states, file, standard out, or standard error. But imagine how many states this object could be in if we were writing Python or Java, right? Or most managed languages, right? What we would do is that we would have file and that would be nullable, right? It might be none or it might not be. We would add the path field. That would be nullable. It might be none or it might not be. And maybe we would represent this standard out, standard error distinction with a flag. Maybe a Boolean flag could be true or false. Something like that. And if we do that, then we have 2 times 2 times 2 is 8 different states that the object could be in. And we can make that work. That's okay. We can get our work done. But 5 of those 8 states are like silly, right? They don't make any sense, right? Like, what does it mean to have a path but be in the standard error mode? It's like, it doesn't make sense. I don't want to be in that state. What does it mean to have a file but not have a path? I don't know. I don't want to think about it. And by defining an enum, we're able to tell Rust, I only want these 3 states. The other 5 possible states we might imagine, just never let my program get into those states. And that's really what allows Rust to see that all these lines of code in our program are no longer making sense in the context of the changes we made. So we're able to like narrow down that state space. Enums are very, very good at that. And I often find that when I move from Rust back to other languages that don't have enums, this is the feature I miss the most. I just get used to it. I just miss it. enums catch a ton of bugs. And once we have them, we use them all over the place. All right. Next feature I want to talk about is destructors. Now, of course, destructors is the C++ term for what we're talking about here. Rust is going to call this drop. So this is the cleanup that runs when we are done with our objects, right? And, we're talking about resources and things, right? So, of course, we're talking about those files. And I want to make this section about answering a question. And that question is, do we need to close this file? So here's the main function of the program we were just looking at. We just saw some of this code. Here's the main function. There's not much to see, right? Command line arguments, and we create the screaming output, and there's some type gymnastics, but it doesn't matter. We have this output local variable, and that's a screaming output, and it might have a file on the inside of it. And my question is, does this variable get cleaned up correctly? Do we close this file? Now, to be fair, this question is academic. It's silly because this is a tiny program. It's about to exit, and when it exits, everything gets cleaned up. So we don't need to know. But we could imagine that this code was running in a larger program that might be running for longer. Maybe this code is in a library, right? We might be more interested in those cases about whether we're cleaning things up correctly. So let's imagine that we're interested in that. And the answer is we don't have to worry about it because output's going to go out of scope. It's going to go out of scope at this closed curly brace down here. And when it goes out of scope, it gets dropped. That's what Rust calls its destructor. And when drop runs in Rust, it's by default, it's automatically going to run here. And when it runs by default, it is automatically going to drop any fields that the object has. That's true of structs, right? Regular objects with many fields. It's also true of enums that have fields. So when the screaming output gets dropped, if it's a file, if it's in the file mode, the file member gets dropped. And we could go read the docs, and we could read the docs for file, and we could see, yes, it says when it is dropped, then it closes the file internally. Great. Okay. So the answer is just, this is already doing the right thing. We don't have to worry about it. I want to take a moment and do a little science experiment. Let's say we didn't believe the docs and we wanted to see the file getting closed for ourselves. I want to do this science experiment because it's going to help us talk about Python in just a moment. How would we convince ourselves that the files are really getting closed? So here's how I do it. I've written some funny code here. We see that this program, when I run it, is just going to print some numbers. Okay, what am I doing? I'm looking at file descriptors. Probably half of the audience has not heard that word before, but when we open files, we're asking the operating system to open them for us. The operating system does some stuff, and it hands us back a number, a little handle for the file. It's kind of like a pointer, but it's not a memory address. It's just a number. It's usually a small number, and that number is the way we refer to that open file handle when we talk to the operating system, when we write to the file, when we close to the file. We use this number under the covers. So that's what the Unix Linux world calls a file descriptor. And okay, so we're printing some file descriptors and we're calling this function 3 times. That's why we see 3 lines here. And each time we print them, we're calling the raw file descriptor method on the file. That's what we print. Okay, these are debug prints. It doesn't matter. And okay, so what are we seeing here? We're seeing 34, 34, 34. So what we're seeing is that we get the same file descriptors every time we open the file. The operating system's reusing the same numbers for these. And what that tells us is that these files got closed. So if these files had not gotten closed, what we would see is 3, 4, 5, 6, 7, 8. Right? We would get here and descriptors 3 and 4 would still be in use. They would not be free, and the operating system would have to use different descriptors. So seeing the same numbers tells us that those files got closed, and we know how, right? These 2 local variables got dropped at the end of the function. Fair enough, right? And now we just see that happening. So my question is, what is the story in Python? And the answer is, it's complicated. So here's the same science experiment in Python, and we see that we get different answers depending on which Python we use. If we use the standard Python interpreter called CPython, right, we see similar behavior. But if we use PyPy, that's a different implementation. Sometimes it's faster. Some companies use it for that reason. We don't see the files getting closed. We see different descriptors. MicroPython, that's the Python that runs on your Arduino little microcontroller or your toaster if you run Python on your toaster. MicroPython, like PyPy, is not closing the files quickly. So folks in the audience who are very familiar with Python might know that the standard Python interpreter does what's called reference counting. It keeps track of the number of references to these guys. So when this function ends, those counts go to 0, and that's how it cleans them up. These other Python implementations do not use reference counting. They use a more traditional garbage collection, and it does the same work, but it does it later. So we don't see it here. Final piece of trivia, final little science experiment. This is very specific to Python, so I won't dwell on it, but it is possible to make the standard Python implementation behave in the same way. So I'll go back and forth so you can see it. So here's back and forth, so you see those numbers changing. Right? So what have I done here? I have created something called a reference cycle. And if you have heard of a reference cycle before, you may be interested to read these 4 lines of code and see, yes, I see this creates a cycle of references that will not go to 0. So this needs to get collected later when the cycle collector runs. If you have not heard of a reference cycle before, don't worry about it. This is trivia. The important takeaway is that even the regular Python implementation, even CPython, does not necessarily guarantee that resources like files are getting cleaned up quickly. And this is why experienced programmers in Python and in any of those managed languages, Java, Go, right, Ruby, they will all tell you that you need to explicitly clean up your resources whenever you write code in these languages, right? We should not rely on the garbage collector to do it for us, because the garbage collector might do it later, and later might be a long time, and the number of files we're allowed to have open at the same time is usually not that big. On my machine, it's about 1,000. Just not small, but not very big, and a long-running program can run into these resource limits if we don't explicitly clean up our resources. So that's the point of this science experiment. So what does that look like? Here's the bare minimum version of this. So we've given ourselves a close method. We remember to check for that null, and then we call it. Now, of course, the experienced programmers in the audience probably immediately recognize my mistake here. So I'm calling close in the happy path, right? If I don't encounter any errors, I'm going to correctly clean up the files here. But the write method could raise an exception, right? Writing to a file could fail. So if I get an exception here, then I'm never going to make it to this line. And if some part of my program is catching exceptions, my program might continue running, but then I didn't do this cleanup, right? So the smallest version of this that is correct uses try finally here. And folks from Java, C++, right? We all recognize this feature, right? This is the exception handling cleanup keywords, and everything in this block will run even if an exception was thrown in this block, right? So this is the first version of the Python code here, my screaming output program, that is correctly cleaning up its resources in all cases. It's not terrible to write, but it's definitely not the lazy way, right? The lazy way is to not clean up at all, and the slightly less lazy way is to only clean up in the happy path. This is what we have to do to clean up in the error case as well. I want to make this example slightly more complicated so that the resource handling situation gets slightly more complicated, and we can see how that feels in Python, very similar to how it feels in all the managed languages. So a lot of code, don't look at it all, but we can look at the terminal on the right. Scream is now scream many, okay. And I have these 3 file paths, and now the output is getting written to all of them. Okay, so I've just gone from having one file argument to many. Fair enough. Let's zoom in on the code. Here's the main code. I have a helper function open outputs that's returning a list of screaming outputs. We'll look at that in a second. We're looping over that list to do the writing. We're looping over the list to do the cleanup. Okay, not terrible. 3 lines of cleanup. Let's look at this helper function. So this is where things get a little more difficult. So in open outputs, the happy path, what this function is doing is very simple, right? Create a list, loop over the paths that we were given as an argument. We open each path and append them to the list, and then we return the list, right? Simple helper function. But the 4-line happy path comes with 5 lines of cleanup, right? So, of course, we don't want to use try finally here because we don't want the cleanup to run if we didn't see any errors. If we're on the happy path and we're about to return these outputs, of course, we don't want to close them. We only want to close them in the error case where we're not returning them, right? So we have to use except. Can't use finally. We have to remember to re-raise the exception. It's very easy to forget this, right? We don't want to swallow the exception. We still want that error to make it up to the higher levels of our program. And if the experienced Python programmers were looking at this code earlier and thinking that maybe we should use a with statement here, right? The with keyword in Python is often very convenient for cleaning up resources. Java has try with resources. C# has the using keyword. Golang has the defer keyword, right? All of these are very useful for scope-based cleanup. We see here we really cannot use the with keyword here. We can't use try finally, right? We can't do scope-based cleanup because we need to distinguish between the happy path and the error case. So this is a simpler helper function, and I think any medium to large Python application probably has dozens of functions that look like this. And it is surprisingly difficult to handle resource cleanup correctly in all cases. For memory cleanup, of course, we just rely on the garbage collector and we don't worry about it. But as soon as we're talking about resources, we have to do it by hand, and that can get a little bit annoying. Let's see how Rust does this. Here's the Rust code. We see on the right, it's the same story. We've got multiple files. I'm going to zoom in to open outputs. What do we see? Some error handling, right? But where's the cleanup code? There is no cleanup code, right? This function is doing all the right things, and it's doing them by default. So this is the lazy way to write this function, and it handles the error case correctly, right? So if this question mark represents an error, right? If we try to open a file and we failed and we get an error here, we're going to return early, and this local variable outputs is going to be dropped at the close curly brace. If we have already pushed any files into the vec, into the list of files, that vec is going to be dropped. It's going to drop all the objects in it. Those objects are going to clean themselves up. That's reliable. That happens automatically. That's the error case. The happy path is even more interesting. So if we return outputs, this is what returning at the end of a function looks like in Rust. You just put an expression here. If we return outputs, then Rust is going to call this a move. So outputs is getting moved to the caller, returned. And because it gets moved, it does not go out of scope at the normal place. So the normal drop-based cleanup that would happen in this close curly does not happen if we make it to this line. Rust understands the difference between dropping local variables to clean them up and moving output out of the function. So the caller will clean this up later. Okay, so that's very convenient. It's very convenient. You're going to handle both cases correctly all the time in Rust. It's very hard to get this function to leak resources. Now, maybe not everybody is as excited as I am about closing files. I think cleaning up resources 100% of the time, every time is great. Maybe most people don't really care about this category of bugs. But I think the most interesting application of this feature is multi-threading. So I want to adapt this into an example of some code that is dealing with data that might be shared with other threads and see how the same feature shows up in that code. Here's a preliminary slide. So I want to get this small little function in our heads. There's no threading here. There's no locks here. This is just a little function dealing with integers. I just want to get it in our heads. What are we doing? Add one to smallest. Okay. We have an argument ints. That's a list of integers. These are 32-bit integers. This is what Rust calls a slice. If you have not seen that, I'm not going to worry about it. It's a list. We start at index 0, and we loop over all the other indexes in the list. At each place, we compare the value of the next integer to the smallest one we've seen so far. And if the next integer is less, it's the new minimum, we update the index that we're storing at smallest index. So at the end of this loop, we have the smallest index in the list, and we do our thing to it. In this case, we said we're going to add one to smallest, so we add one to it. Okay, so this is a loop that finds the minimum. I think we've all written code like this in some language. That's the structure of our code. Now let's see this work with locks. So I've thrown a bunch more onto the slide. The structure is the same. We have a list of ints. We start at index 0. We loop over the other indexes. We do a comparison at each place. We update the minimum, and we use it at the end. So the structure is the same. What have I done? This list, instead of just being a list of ints, is a list of mutexes. So a mutex, a lock in Rust, contains the data that it locks. So this is a list of locks, and each mutex lock contains an integer. Okay. And then when we call lock, I'm going to mostly ignore unwrap here. I'm just going to think about lock. When we call lock, we get this mutex guard. And the C++ people know what's up here because one of the jobs of the mutex guard is exactly the same as in C++. So when this guard object goes out of scope, when it gets dropped at the end of its block, it's going to unlock the lock that it came from. Okay, so that's the cleanup, right? That's the unlocking. Cool. We don't have to remember to do that. It's just going to work. The other job that mutex guard has in Rust, because the mutex contains data, the mutex guard acts like a reference to that data. So we see here when we compare the integers, we use the star operator. And if you're coming from C or C++ or Go, that's familiar, right? That's the pointer dereference operator. If you're not coming from one of those languages, don't worry about it. We can just remember that the guard is acting like a reference to the integer. So we compare the guards to compare the integers inside of them. And then when we add 1 to the smallest integer, we use the guard as the reference that we add 1 through. Okay. Why have I gone through all the trouble of putting this on the slide? I want to think together about where the mutex guards get dropped. So where does the unlocking happen? We already mentioned half of it. So this mutex guard, smallest guard, gets dropped here at end of scope. Fair enough. So when this function exits, we will unlock the last guard. Makes sense. What about this guard? What about next guard? By default, next guard would go out of scope here at the end of its block. So that's the end of the body of the loop. By default, next guard would go out of scope there, and we would unlock whatever mutex that was each time through the loop. However, this example is more interesting because if we make it to this line, then we are doing another move. So just like returning that vec by value was a move, assigning these guards by value is a move. So we are moving next guard into smallest guard on this line. And that does two things. Like we were talking about before, it means next guard is not going to get dropped at this closed curly. If we make it to this line, it's not going to get dropped here because Rust can see that it was moved away. It's not going to get cleaned up in this block. Also, if we're going to move next guard into smallest guard, we have to clean up the guard that was previously there, right? We don't want to just forget about it. So we drop the previous value of smallest guard automatically as part of that move, right? So each time through this loop, we do drop some mutex guard. We unlock some mutex, but which mutex it is depends on which code path we take. If we take this path, the block that we're going to drop is the previous value of smallest guard. But if we don't take that path, at the end of the loop body, we drop next guard. So the unlocking logic here is actually very subtle. It's invisible and subtle, and we're only ever holding 1 or 2 locks at any given time, and they're all getting unlocked automatically. And that's really cool. Like, it's cool that this is all automatic, but like, it's also a little scary, right? Because if we've written multi-threaded code before, we're used to all the mistakes that we can make, the deadlocks and forgetting to take locks and things like that. And we might be pretty worried looking at this and being like, whoa, like, you know, do I want this to be invisible? This is surprisingly subtle. And the best thing about this is that Rust is going to catch the mistakes that we make when we write this code. So here's an example. I just swapped these for no reason. I imagine it's a typo or I fell asleep while I was writing the code. So now instead of moving from next to smallest, I'm moving from smallest to next, which doesn't make sense. And my algorithm is broken and I'm going to get the wrong answer. More importantly, Rust agrees that it doesn't make sense. Rust is going to see this as moving out of smallest more than once. And it's going to see it as using smallest after we've moved out of it, even though we didn't put anything there. And Rust sees that, and Rust knows like, this doesn't make sense. You can't move out of an object more than once. You can't use it after you've moved it away. We're just not going to compile this. And understanding exactly what this error is saying, that's a learning tax, right? We have to learn about move semantics and how they work. But if we make the mistake, then we can be confident that our code's not going to compile. And that is very different from how most other languages deal with multi-threading. We usually have to do this stuff in our heads. Here's another example. This one's heavy on the syntax. So if you have not seen dereferencing and referencing combined in Rust, this might not make a ton of sense. We can just look at this type to kind of see what's going on here. So here I'm getting that mutex guard, but I'm immediately reaching through it. And I'm trying to get a reference directly to the integer that's inside of it. I'm allowed to do this. This is valid syntax. But my mistake is that now that these variables, I didn't rename them because I'm calling this a mistake. My mistake is now that these variables are just references to the inside, when I do this move, I'm only moving the reference. I'm not moving the guard that came out of this part of the expression. So in this case, because of this mistake, the next guard actually always goes out of scope at the end of the block, at the end of the loop body. And that would mean that if I assigned that next reference to the smallest variable, that reference would outlive the guard that it came from. So that would be a mistake. That might be exactly the kind of mistake we were worried about when we started thinking about mistakes we can make in multithreading. This would be trying to use a reference after the lock that we got it from has already been unlocked. And what we see here is that Rust catches that mistake every time. We just can't make that mistake in Rust. And what's very interesting about this one is this is the borrow checker. So you may have heard of the part of the Rust compiler called the borrow checker. And usually we talk about the borrow checker when we're talking about C and C++ bugs, right? The borrow checker helps us catch those dangling pointers and things, these memory corruption issues that come up in C and C++. And in garbage collected languages, we don't usually think about those mistakes. We just expect the garbage collector to handle them for us. But when it comes to resources, and we're doing this cleanup manually, we're not relying on the garbage collector to do it because the garbage collector doesn't do it soon enough, then that raises questions about what might happen if we hold onto a reference to some object that we've explicitly cleaned up, right? That is a type of bug that you can write in managed languages, right? You can try to use a file after you've closed it, things like that. And they come up sometimes, they don't come up all the time, but you could imagine if Python or Java had moved semantics like this and sort of dropped semantics like this, where cleanup was just happening automatically all the time, it would be very easy to accidentally hold on to a reference to some object that's about to get cleaned up. That would be very confusing. And I think that's why we don't see any features like this in managed languages. There would just be too many bugs. We see this in C++, and of course, C++ is famous for the difficult bugs that result from holding on to pointers to objects that have already been destroyed. So the borrow checker, yes, it's mostly solving C++ bugs to do with memory, but it's also solving the same bugs in a different flavor to do with resources. And that's what lets Rust get away with this very aggressive, very automatic, very invisible resource cleanup. Because if you make a mistake, the compiler's going to catch it. We're not paying a bug tax in exchange for these features. We're paying a learning tax, that's true. But in exchange, we get code that does not have any resource leaking bugs, does not have any use the resource after it was already freed bugs. And the resulting code is really nice and compact. And when I move from Rust back to a language that requires explicit cleanup of resources, I often miss this. All right, so that's destructors. All right, the last big section, aliasing rules. What is spooky action at a distance? Well, it's a metaphor from quantum mechanics, but it's this bug, right? We've all written this bug. What have I done? I've got a person. Each person has favorite foods. Okay. Everybody likes donuts. So when I create Alice, I give her the list that just has donuts, but Alice also likes apples. All right. Now Bob likes donuts too, because everybody likes donuts, but Bob also likes bananas. And then after I've done that, I'm going to print their favorite foods, and I expect to see Alice likes apples and Bob likes bananas. But what do I see? Everybody likes apples and bananas. I think we've all written this bug. Why did this happen? This is why it happened, right? We used the same list in both places, and everything in Python, just like in most managed languages, is pass by reference. So both people, Alice and Bob, get a reference to the same donuts list. So when we were appending to the two different lists, we were actually appending to one list. There's only one list in this program, and we were printing what we thought was two lists. We were just printing the same list twice, right? Spooky action at a distance, right? So mutating one thing secretly under the covers has mutated this other thing, right? This is a big category of bugs. We all make mistakes like this all the time. The fix is well known. I think anybody who's got a year or two of Python experience, a year or two of experience in any of these languages knows the fix. We need to copy the list, right? So this is one way to do it in Python. The square bracket syntax is another option. Different ways to copy the list. If we copy the list, we fix the bug. Okay, fair enough. I want to highlight just a minor point here. This fixes the bug in this case because strings are immutable. But in a more complicated case, we might be dealing with a list of lists, or a list of dictionaries, or a list of people, list of person, right? And if we have mutable objects in our list, then copying the list doesn't necessarily fix the problem. It only copies the top level of the whole data structure. It's a shallow copy. So again, this is a simple example. This is good enough for this case. This is not a deep copy, though, and sometimes we have to remember that. All right, let's look at the same bug in Rust. Let me skip through the code and just look at the fix. The fix is the same, right? we copy the list. And just like in Python, this second copy is optional. We could just use donuts here, but the first copy is the important part, right? This fixes it. Rust calls this clone that fixes the bug. And I like to point out here that if we had a vec of vec, if we had a vec of hash map or a vec of person, right, this clone would be a deep copy. So we do not have to worry about a shallow copy failing to fix more complicated bugs. That's a subtle thing. We don't have to deal with that in this example. What I want to highlight in this example, if I go back to the code that did not have the fix, this version, this is the same bug, right? This is trying to make the same mistake that we made in Python. Here in Rust, this code does not compile, right? Rust will not let us run this code. Rust sees that this is a move and this is a move, right? It's just like outputs. It's just like those mutex guards. We've moved donuts into Alice's favorite foods. And so when we try to move donuts again, Rust is like, can't do that. You moved it away. If you can't move it twice. If you can, you could move it out of Alice because that's where it is now. But there's no longer any value here in the donuts variable. It's been moved away. You cannot move that variable again. It just doesn't compile. Now, there are other ways in Rust that we can try to make the same mistake. So here's Rust trying to do the same thing that Python does. So of course, not everything in Rust is by value. So like C, C++, and Go, we have values and we have references or pointers, right? So here's trying to create the same problem with references. So this version of the code is trying to do exactly the same thing that we were doing in Python, right? We got two references to the same list. And you can do this in Rust. These are shared references. You can create multiple shared references to the same list. That's why they're called what they're called. But this code is still not going to compile because the next line fails, right? The rule in Rust is a shared reference behaves like what C or C++ calls a const pointer. So you usually are not allowed to do mutation through a const pointer. You're not allowed to do mutation, usually, through a shared reference. And so when we try to push into favorite foods, that line fails, right? We can create these references, but we can't use them to do mutation, right? So we cannot write this bug. This code does not compile. Now, of course, sometimes we do want to mutate things through a reference, right? We don't only want const pointers. We want our non-const pointers, right? Rust has that. That's called mutable references. So here I'm trying to reproduce the same mistake using mutable references. Now, if I have a mutable reference, this line is legal. I am allowed to push through that. But now this line is illegal again. So it's a different rule. It's sort of like the move semantics rule, right? We can't move from the same value more than once. Mutable references do not move the values they point to. They're just borrowing them. They just point there. But the rule with mutable references is they're not shared. They must be unique. You are not allowed to have two mutable references that point to the same object at the same time. You can't have a mutable reference and a shared reference either. The mutable reference has to be the only one for as long as it's borrowing the object. And so we see this error here. This mutable reference here is inside of Alice. Alice is still definitely kicking around, right? We still have that. Rust can see that. We're not allowed to create this second mutable reference here, right? So, there's a lot going on in Rust, right? Move semantics and lifetimes. There's a lot to think about. There's a lot of different ways to try to make the mistake. And there are learning taxes that we pay here as we learn about all these features of the language. But the important thing here, the repeated theme, is that when we make mistakes with this stuff, the compiler catches those mistakes. The bugs don't show up at runtime. They show up at compile time. A couple other versions of the same mistake. What have I done here? I've given person an add favorites method. So we take some other person, we loop over their favorite foods, and we add each one to our favorite foods. We're just copying their favorites. And I create Alice, and she likes apples, and then I make a mistake, right? What have I done? I've called add favorites on Alice with Alice. And in this case, what this does in Python is it's an infinite loop that runs forever, and it keeps growing and growing and growing that list until all of the memory on my machine is exhausted. My entire 8 gigabyte memory space is holding, I don't know how many, a billion pointers to the string apples, and then eventually Linux kills my process. Right? That's what happens. A lot of languages would call this mistake an iterator invalidation mistake. This does cause a lot of memory corruption in C++. And unfortunately, we are allowed to do this in Python. We're allowed to iterate over a list, even though we're changing the length of that list. And that is usually not what we want to do, right? I think this is a bug that anyone with a couple years of Python experience has probably written. It's interesting that if favorite foods was a dictionary, like a hash map, Python would not allow this. This would crash immediately. You are not allowed to loop over a dictionary while you insert or remove keys from that dictionary. But they don't have the same rule with lists. We can write this bug. Of course, we cannot write this bug in Rust. And we now know why. So when we try to write this line, and there's nothing wrong with this helper function, but when we try to write this line, we're taking a shared reference to Alice, right? That's the other person. And we're also calling the method on Alice, which implicitly and automatically takes this mutable reference to self, and self is Alice in this case. So this mutable reference and this shared reference are referring to the same object. Those are both Alice. Rust can see that. That violates the no mutable aliasing rule. So Rust just doesn't compile this code. There's a whole category of subtle bugs in C++ that has to do with collections, like data structures, that copy other collections or move from other collections. And this question of whether self and other can be the same object, because if you don't think about that, it's very easy to have really tricky bugs in that rare case. It's quite nice that in Rust, this just can't happen. It is completely illegal for self and other to ever refer to the same object because self is a mutable reference. The compiler will not let you do it. Last version of the same bug. This is the lambda or closure version. Again, I think everybody with a few years of experience in any language that has lambdas has probably written this bug, right? So I'm looping from 0 to 9, and I'm building this list of functions that in theory, maybe I intended them to print the numbers 0 through 9, but when I actually call them, they all print 9, right? And they all print 9 because they are referring by reference to this variable in the calling scope, or the defining scope, I guess. And that variable is changing, and they all end up referring to its final value. The value is 9. I think Golang 1.22, which came out earlier this year, if I have the version right, they fixed this bug by changing the language spec definition of what for loops do. Like Golang before this year, you could write this exact same bug. And after this year, if you're using the latest version, you will see 0 through 9 here because they changed for loops. This bug was so common that 14 years after the release of Go 1.0, they changed how for loops work to fix it. This is a fairly common bug, and we should not be surprised that in Rust it doesn't compile, right? That's the theme here. This doesn't compile. So in this case, this lambda. This is sort of like the parentheses of the closure. This is the arguments going here. There are no arguments in this case. But it's capturing I from the outside. In this case, it's a borrow checker error. It's a lifetime error. We could also imagine this being a mutable aliasing error, right? If the I variable lived for the entire duration of the loop and we were trying to reference it while it was being mutated, that violates the mutable aliasing rule. It doesn't compile. Now, the fix for this code in Rust is the move keyword. And that's not obvious. I think the first time you learn it, like in cases like this, it's a little bit confusing because we're not really moving the integer, we're copying it, right? We want each closure to get its own copy of the value of I at the time the closure was created. That is what this does. It's a little bit non-obvious that this is what it's called, and this is a learning tax that we pay with Rust. There's things we have to learn. But this fixes the code. And the important thing is not that this is obvious. Again, I don't think this is obvious. The important thing is when we made the mistake, this is the previous slide, it didn't compile, right? So all these bugs that we have to put in time and effort to catch in all these other languages, the compiler catches them for us again. And once again, end of this section, I think the most interesting version of this is in multithreading. So here's a quick multithreading example. I'm looping over the numbers from 0 to 99. I'm not using a for loop here. I'm using like a fancy iterator feature that the Ruby programmers are probably very familiar with, right? And we're adding up all those numbers and we're asserting the answer. And I'm writing it like this because this way of doing it makes it very easy to multi-thread this. So I'm going to add in a library called Rayon. This is a library that helps us do threading. And Rayon gives us this very magical helper method here into parallel iterator. So this changes the iterator into Rayon magic. And this for each method on the Rayon version of the iterator runs the body from many threads at the same time. So this just magically and automatically multi-threads the loop, which is pretty cool. Obviously, this is a toy example. It's not doing enough work for us to want to multi-thread anything. But in this toy example, it's very cool that it's this easy to multi-thread the loop. Unfortunately, it's broken. It's broken because if you have multiple threads trying to add to some at the same time, they're like multiple ATMs in your bank balance, right? They read the bank balance, they add the number, they write the bank balance, but they were just writing at the same time. They're stomping on each other's work. You get the wrong answer, right? So anyone who's played with threads has probably seen issues like this. We should have locked this, right? If there are multiple threads that are going to touch this, we need a lock. We forgot that here. We're going to get the wrong answer. And in fact, in the native languages like Rust and C and C++, it's not just the wrong answer, right? This is a data race. Data races are undefined behavior in these languages, right? So this is a common category of bugs. And Rust sees it. Rust catches it. And we don't have time to get into all the machinery of the traits that these closures implement and exactly how Rust sees it. But suffice it to say that Rust sees this closure capturing a mutable reference to some, but then it sees that closure being used in a place that wants to share it with many threads. It can see that through the types, and Rust catches this. To fix this, we put mutex in here. And we saw mutex before, and folks who've used mutex in Rust can read this code. I think if you're seeing mutex in Rust for the first time in the last section, it's probably moving a little too fast, and you have to slow down and read each line to see exactly what we've done. But the important thing is, if we throw mutex in there, the code will compile. So Rust can see that this version that locks the integer every time it's trying to add to it, and then locks the integer when it's trying to read it at the end, this code is correct. It's silly, right? It doesn't make sense to spawn a lot of threads if all they're going to do is wait on the same lock. It's a silly example, but the important thing is Rust can see that the code is correct. So a lot of Rust programmers refer to this as fearless concurrency, right? So you can write multi-threaded code and be very confident that if it compiles, not saying you have no bugs, but these data races, these really nasty bugs where you forgot to lock the thing you were supposed to lock, those get caught at compile time. You just don't have to worry about them. And if you're writing multi-threaded code, the weight that comes off your shoulders when you don't have to worry about this stuff, it's a lot. The feeling of trying to write multi-threaded code in other languages when I've gotten used to doing it in Rust, I miss this. This catches so many bugs. So we've been talking about the managed languages. I also want to talk about the functional languages, right? So there's this category of languages: Haskell, OCaml, Scala, Lisp, Scheme, right? Some of us learned one of these in school. Most of us don't use these at work. Some people do. These languages were famous for catching the same bugs for a long time. They do. These languages also catch this entire category of bugs. But they do it with a very big hammer. So the functional programming languages say that, yep, we're gonna free you from worrying about this entire category of spooky action to distance bugs, and we're gonna do that by saying you never mutate anything. Approximately. Haskell is pretty strict about that. Other languages are not necessarily totally strict about that, but they discourage mutation. They use a lot of recursion. There are a lot of learning taxes that you pay to use these languages. There are a lot of performance taxes that you pay to use these languages, right? Normal sort of for loops over a list, change the list. You have to write those differently. There's a lot of learning and coding taxes that you pay, and you do catch all these bugs. And so for a long time, this was kind of the biggest sort of advertised feature of this category of languages, these functional languages, catching all these bugs. And I think Rust represents a sort of third way here. So Rust is catching all the same bugs, but it's not using that big hammer. It's not saying no mutation. You can do all the mutation you want in Rust, but you cannot do aliasing while you are doing that mutation. So you can alias sometimes and you can mutate other times, but you cannot do both at the same time. So it's sort of like having two smaller hammers instead of one big hammer. And this rule is absolutely the hardest part about learning Rust. There are programs that you're used to writing in Python or Java or Go or Ruby that are not legal in Rust, and you have to restructure them. And there's a lot of learning there. But you're getting the same payoff. You're getting that entire category of bugs just erased. And you're paying the learning tax, but you're not paying the performance tax. So in many cases, you're not paying the coding tax. You can write code that feels normal and natural most of the time. And so it's sort of a middle way between all the popular languages that have all these bugs and the functional languages that eliminate these bugs at a great sacrifice. Rust is able to kind of thread the needle there. And that's very exciting. And I think this is the other half of the story. Not just multi-threading bugs, but that's a big part of it. But this category of bugs, and in fact, all the categories of bugs we were just talking about. Rust makes them go away. And it does that without making big sacrifices in the final code that's generated. And we make the sacrifices when we learn the language and when we're trying to write code that Rust will accept. But the final code is small and clean and in many cases easy to read, right? That open outputs function was very easy to read. And we get these correctness benefits. So it's a different trade-off, and it's in many cases a more attractive trade-off. And it's a trade-off that can make sense even if we were considering using Python or JavaScript or Ruby, right, for our project. This is a trade-off that we can consider making if we're willing to spend that extra time writing the code. It can help us get our work done. So I think that's the other half of the story of why Rust is as hyped as it is. One little closing thought I want to leave everyone with is little bonus slides. So the thing that we maybe most famously use Python for, even in projects that aren't written in Python, is little standalone scripts, little utility scripts. I'm not even going to go through this line by line. Just here's a little echo script that screams at you, and you can write that in Python, and it's a standalone file, and it has no dependencies, and you can use this in any project to do whatever you want. I think many of us who write Go or Java or even Rust every day still have a lot of these little utility scripts, these little Python scripts in our projects. You can do things like this in Rust, which is kind of fun. Today, it's a little weird. You have to take this extra dependency Rust script. It's not standard. You get part of a cargo.toml manifest here. Not all the features, though. So it's non-standard, and specifying things like what Rust addition you want to use, it doesn't work here. So I wouldn't use this in production. You could play with it today. But there is a feature coming down the road. An RFC has been accepted, right? A future change to language that will eventually, this doesn't work today. This only works on nightly today, and you need some extra noise here. But eventually, you will be able to write this. And you can use Cargo almost like an interpreter for your program. And just like the previous slide, it'll automatically build the thing when you run it the first time. And you can have the entire cargo.toml syntax here. And you can take all the dependencies you want. And it's going to work with Rust format. And it's going to work with Clippy. And it's going to work with Rust Analyzer. And all of the Rust tooling that we normally use with regular Cargo projects. It's all going to work here. And this is actually going to be a viable option in production for little one-file scripts. And I'm not saying that I would write all my one-file scripts in Rust. That can be a lot of trouble sometimes. The build time can take many seconds. Right? But I do think it is interesting to consider using something like this when you have a Python script. It's not going to be very much code, but maybe it's growing, and it needs to start taking dependencies. And taking dependencies when you go from a one-file script with no dependencies into having dependencies in Python is very painful. That's painful in a lot of languages, right? You need to worry about virtual environments, and now your workflow is different and things like this, right? And when you're looking at a Python script that's going through that transition and considering taking on all that pain, in that moment, I think it might someday be interesting to consider rewriting that script in Rust. Right? The script is probably not very much code, but its callers don't want to have to know about the change. And Rust will give you that option. The callers don't need to know. You might change .py to .rs. They might know that. But the callers don't necessarily have to know that anything has changed here. It will just work. And you can take all the dependencies your heart desires, and you can grow the complexity of the script as needed. I think that will be an interesting place where future Rust, once this feature is stabilized, future Rust might start worming its way in to some of the use cases where we use Python, kind of like it's been worming its way in to C and C++ projects, rewriting one function at a time kind of thing. So I think that'll be an interesting part of the Rust story going forward. Watch this space. And I think that some of that hype that Rust has been generating, I think, its usefulness in all these little areas that we've normally used lots of different other languages for, I think it's a big part of that hype. And I'm looking forward to this. All right. Thanks for listening.